Okay, this is the first video in a series of videos on topic 1.5, which is atomic structure and electron configurations. So first, what is an electron? Of course, hopefully all of you took chemistry 1 and we understand that the electron is a negatively charged particle that is involved in chemical reactions, right? So all chemical reactions involve the transfer and movement of electrons, right? Or we wouldn't have any periodicity or anything making, combining, reacting at all. So we have two different equations that we need to know for this course. We have the speed of light equation and the wave energy equation. Hopefully, again, you've worked with these in chemistry 1. You feel pretty confident, but this is a little refresher if not. So c is the speed of light constant. So that's 3 times 10 to the 8th meters per second, and that's equal to the wavelength, usually given in nanometers, but not always, times the frequency. So this is a sinusoidal curve. We have our wavelength, which is here to here, and then that's that. And then our frequency is 1 over a period, 1 over p, which then combined together is always going to equal 3 times 10 to the 8th, because it's speed of light, and we're calculating usually a solo photon, but it doesn't have to always be a photon. It could be a mole of photons, a mole of, whatever, half a mole, it doesn't matter. And then the wave energy equation, we have E, which is energy, which is equal to Planck's constant, 6.626 times 10 to the negative 34th joules per second, times the frequency, right? So we see that our frequency is the thing that unites these together, and if we know our wavelength or our frequency, we can solve for the other variable, because remember, C and H are constant. So let's work on a practice problem. So let's calculate the energy of a photon given that the wavelength is 436 nanometers. Okay, so immediately what jumps out to me is that we know our wavelength, but we're looking for energy. And remember, wavelength isn't our energy, so we're going to have to use this first equation first. So we're going to say 3 times 10 to the 8th, which is, remember, our speed of light constant, is equal to our wavelength, which that's like a Greek lambda. Sorry, I'm not too good at Greek. And then we know our wavelength, so this is going to be equal to 436 nanometers, which a nanometer is 10 to the negative 9th, so I'm going to rewrite this as 4.36 times 10 to the negative 9th meters, because this is meters per second. So we're going to set, then we're going to times that by our frequency, because we need to find out our frequency. And so then we have, bust out the handy dandy calculator, we have 3 times 10 to the 8th. Then we're going to divide it by this wavelength of 4.36 times 10 to the negative 9th meters. Our meters cancel out. So we have 3 times 10 to the 8th divided by 4.36 times 10 to the negative 9th. And we get a frequency of 6.88 times 10 to the 16th. Of course, they gave 3 sig figs here, so I'm going to leave my answer in 3 sig figs. They gave 436, so I'm going to leave mine as 6.88. Remember, scientific notation, that's our number of sig figs. So now we know our frequency, and we know Planck's constant, so we can solve for the energy pretty easily. So so we're going to say that the energy is equal to Planck's constant, which is 6.626, which is the Stitch number is what I like to call it, from Lilo and Stitch. So we have joules per second here. Be careful that you watch your units. And then our frequency is going to be, well, this was 1 over, so this is, right, so we cancel our meters, so we're going to have 1 over a second. So this frequency is equal to hertz, which is really equal to inverse seconds, and you could call it 1 over a second, right? Because a negative exponent of 1 means that it gets dropped down to the denominator. And then we are just going to use our frequency we just calculated, so we're going to do 6.88 times 10 to the 16th, and we're going to say just for simplicity, we'll say 1 over second so you can see it canceling out. So we're going to have second times 1 over second, and then our energy will always be given in joules, especially for this kind of problem. Sometimes we'll use kilojoules, but the metric energy unit is the joule. Then we're going to do times our frequency we just calculated. Pretty simple calculations as long as you understand the variables present. And our energy from our single photon with a wavelength of 436 nanometers equal to 4.56 times 10 to the negative 17th. Joules. Awesome.